Our topic of discussion today is functions, specifically hyperbolic functions. So whenever we're looking at a function, it's important to be able to identify that function by its shape. So whenever we are dealing with a hyperbolic function, they basically look like curves in opposite quadrants. So if we are looking at a hyperbolic function for when a is positive, that would be in quadrant 1 and quadrant 3, and our shape would look something similar to this. Now keep in mind that this is a decreasing shape or a decreasing function, because as the value of x increases, the value of y decreases. So as the function moves to the right, as the value of x increases, the value of y is decreasing. So another way to think of it is that as the value of x, or as the graph moves to the right in the x quadrant or in the x-axis, our value of y starts to decrease, so our function goes into the negative y-axis. Now if we look at our second shape, this is when our function is increasing, when we have an increasing shape, which means as x increases, y also increases, and this is when a is negative, when a is less than 0. So another way that you can remember this is that if you can think of opposites, so when a is positive, when a is greater than 0, there's a decreasing shape. And whenever a is less than 0, or whenever a is negative, there is an increasing shape. And when a is negative, our function is in quadrant 2 and quadrant 4. So as you can see, whenever x increases, or whenever our function moves to the right, our value of y increases, or our value of y goes up. Our function goes into the positive axis, or higher towards the positive axis is another way you can think about it. So if a is less than 0, it's going to be in quadrant 2 and quadrant 4. So let's zoom out for a moment and have a look at the difference between the two shapes. So to quickly summarize, or to recap, whenever a is greater than 0, we have quadrant 1 and quadrant 3, and our function is an decreasing function. Now whenever a is less than 0, whenever a is negative, we have our function in quadrant 2 and quadrant 4, and our function is an increasing function. So let's move on. Now, point number 2 is what each variable, or what each term within our function's equation represents. So a hyperbolic function is represented by the equation y equals a over x minus p plus q. So our y and x represent our x and y coordinates, our x and y values that we will get, or that are given to us from our function. Our value of p represents our vertical asymptote, an asymptote being a line or region on a graph that the graph does not exist, or that the graph does not touch. And q represents our horizontal asymptote. So a quick representation of our different asymptotes. If we have this axis over here, and as an example, we have p equals to 2 and q equals to, let's make it -1. So keep in mind that p represents our vertical asymptote, and Q represents the horizontal asymptote. So a vertical line is just a line from north to south, or if you want to think about it in a different way, when we stand up straight, we are in a vertical position. So a vertical line is basically these lines over here. Or you can think of it as your y-axis. Your y-axis is a vertical line. Now, as you can see, all of these vertical lines always cut the x-axis. So our value of P represents the X value. So let's just erase this quickly. We were told that, or our example was that P is equal to 2. So let's make this point here 2. So if we want to draw our vertical asymptote, we would just have a vertical line that cuts X at 2. And to label this line, we can label it as X equals 2 because it cuts X. Now, our Q asymptote, which is our horizontal asymptote. Now, always keep in mind, horizontal lines are similar to our x-axis, or if you want to think about it in a different way, if you're lying down or if you're lying on your bed, you are then in a horizontal position. So these are our horizontal lines, and as you can see, all these horizontal lines cut our y-axis. So that is why Q, or our horizontal asymptote, is associated with y values. Now, -1, let's make -1 here, and then we can draw our horizontal asymptote like that. And we can label this y equals -1. Now, as you can see from the asymptotes, there's 4 quadrants that have been created. Let's not look at our axis to determine our quadrants. Let's look at our asymptotes to determine our quadrants. So we know that the quadrants are basically the regions that our graph are going to be drawn in. So if we have a graph that's a greater than 0, so let's assume that our graph is a greater than 0. We are then going to have quadrant 1 and quadrant 3 as the areas in which our graph is drawn in. So our graph would basically look something like this. Now, a different representation of our asymptotes P and Q could be extracting them from the equation that is given. So, for example, if we are given the equation y equals 1 over x minus 2 plus 3. Now, we need to extract our P and Q values. So, the easiest one to extract would be Q. We can see the position of Q and we can see the position of our 3. Now, Q is just a constant after your function, or it could be before your function depending on how the question is structured. So from this we can automatically state that Q is equal to 3. Now P is a bit trickier to extract from the equation because you have to take the opposite sign. So as you can see, we've got the x, we've got the x. We've got a negative sign, we've got a negative sign. So P would then be 2. So P equals 2 in this case. Now some people might be wondering, why is P 2 and not -2? Because the equation has x minus 2. Now the reason is because the negative comes from the function or from the formula itself. So for example, if we have x minus p and we need to substitute p as 2, we would end up with x minus 2 after we substituted p. But if our formula is x minus p and we need to substitute negative p into our formula, we would then end up with x plus 2. So let's do an example. Substitute negative 2, we would end up with x plus 2. Now, an alternative way of subtracting p would be to create an equation. So let's do that quickly. So if we look at our denominator of our fraction, x minus 2, all we can do is we can equate it to 0. So x minus 2 equals 0. From there, we solve and we know that x equals 2. So that is an alternative way of extracting our p-value. So therefore, because x equals 2, that's the value of our p. An alternative way is to just extract the opposite sign always. So if you have x minus 2, your p-value would be positive 2. If you have x plus 2, your p-value would be negative 2. Now let's do a different example of p whereby we've got x plus something. Let's use x plus 1. So this time we have a positive value between, or rather a positive value after our x. So the easiest way that I like to use is to just take the opposite value that's given. So because you were given positive 1, you can just extract the opposite value. So if the sign is positive, you'll extract a negative. So therefore p will be equal to negative 1. An alternative approach that you can take is what we did previously, to have x plus 1 and equate it to 0. So whatever you have in your denominator position, just equate it to 0, solve for x. Therefore, you'd end up with x equals negative 1. So you can conclude that your p-value is negative 1. An alternative approach would be to take out a negative, or to factorize a negative. So because you have x plus 1, you can now take out a negative from positive 1. So you can have x minus negative 1, because we know that negative times negative gives us a positive, so we can break up positive 1 into negative 1. So if you look at the shape, or rather the position of this, x, x, negative, negative, and then p. So from this you can also conclude that p equals negative 1. So there's 3 different methods, or 3 different approaches that you can use to extract your p-value. The first being, you can just take out the opposite sign to what is there. So if you have a positive, you'll extract the negative. If you have a negative, you'll extract the positive. The second method that you can use is to equate the denominator to 0, solve for x, and that will be your p-value. The third approach that you can use is just to break up positive into negative times negative, and extract that negative p-value. If you had a positive value, I don't think we used the third approach when we had positive p. So let's have x minus 1. If we were to break this up, it would just be x minus and positive 1. Because we know that negative times positive gives us the negative 1 that we had above. So from here, we know that p is positive 1. Positive 1. So just a quick recap. If we are dealing with p, if we are trying to get our p-value from our equation, we can just take out the opposite sign to what is given. If we want to extract the q value from our equation, we just take it as is. So if it's positive 3, we'll take positive 3. If it's negative 3, we'll take it as is, negative 3. So extracting q is much easier. The only tricky part is dealing with p. Now let's discuss our horizontal and vertical shifts. So P is our vertical asymptote, and it's also our horizontal shift. So a horizontal shift is just to move either left or right. Now, a vertical shift can be to move up or down. So that's basically it. So our p-value is our vertical asymptote and our horizontal shift. A q-value is your horizontal asymptote and your vertical shift. Now, let's move on to point 3. So point 3 is finding intercepts. So we know that whenever we are finding intercepts, if it's an x-intercept, we'll substitute y as 0 and solve for x. If it's a y-intercept, we'll substitute x as 0 and solve for y. Now, an x-intercept is the point on the graph where the function cuts the x-axis and y is 0 at that point. A y-intercept is where the graph cuts the y-axis and x is 0 at that point. So let's do a quick example. So we have the function f of x equals 1 over x minus 2 plus 3. So let us first start with the x-intercept. We know y is 0. So we've got f of x equals 1 over x minus 2 plus 3. From here we know that y is 0, which is f of x. So we substitute 0 and we bring down our function as is. Now we can take our positive 3 to the left and it will become negative 3. That gives us 1 over x minus 2. From this point we can cross multiply. So our denominator on the right multiplies with our numerator on the left. And negative 3 is just over 1. So that 1 will multiply with the 1 on the right. So we have negative 3 into x minus 2 equals 1 times 1, which is just 1. From here, we can divide both sides by negative 3, or an alternative option would be to multiply the negative 3 into the brackets, whichever is acceptable. An alternative approach would have been to swap the positions of negative 3 and x minus 2, which would have resulted in x minus 2 equals 1 over negative 3. So what I'm going to do is multiply into the bracket. So I have negative 3x, and negative 3 times negative 2 gives me positive 6 equals 1. I'm going to take my positive 6 to the right rather, and that will give me 1 minus 6. What I want is all of my variables on one side and all of my constants on the other side. Now, from here, I'm going to bring down my negative 3x, and 1 minus 6 gives me negative 5. From this point, I can divide both sides by negative 3, and I therefore have my value of x as positive 5 over 3, because negative divided by negative is a positive. Now, my coordinates of my x-intercept are 5 over 3 and 0. Now, let's find our y-intercept. So our y-intercept is a bit easier to deal with. So when we're finding our y-intercept, all we do is substitute x as 0, solve for y. So we have f of x equals 1 over x minus 2 plus 3. From here, we substitute x as 0. So 1 over 0 minus 2 plus 3. Can put this onto our calculator. That's going to give us 1 over negative 2 plus 3. And can put this onto your calculator. And you should end up with 2.5 or 5 over 2. So can conclude that our y-intercept is 0 and 5 over 2, or you can write it as 2.5, whichever you prefer. Now, a quick recap. If we want to find our x-intercept, we substitute y as 0, solve for x. If we want to find our y-intercept, we substitute x as 0, solve for y. Let's move on to our next point, which is point number 4. Let's do 4 and 5 at the same time. So with 4, we're dealing with domain. With 5, we're dealing with range. Now, domain is all the x values that the graph touches, whereas range is all the y values that the graph touches. So when we're dealing with hyperbolic functions, I feel like those are the easiest ranges and domains to obtain. So it's a set formula. X is an element of real numbers, whereby x is not equal to the value of p. All we do is we substitute that value of p into this formula. For example, if p is -1, our answer would be x an element of real numbers where x is not equal to -1. Now, when we're dealing with range deals with all the y values that the graph touches. So a hyperbolic function touches all of the y values except the y value at the asymptote, which is q. So our formula would be y an element of real numbers where y is not equal to the value of q. So if the value of q was 5 in this case, our answer would be y an element of real numbers where y is not equal to 5. So let's move on to point 6. So this is actually supposed to be a 6. So point number 6 is axis of symmetry. So we have two axes of symmetry. There's one with a positive gradient and there's one with a negative gradient. So our axis of symmetry with a positive gradient just basically looks like a positive linear function, whereas our axis of symmetry with a negative gradient looks like our negative linear function or negative gradient linear function. Now the steps that are involved when we are trying to find our axis of symmetry is we need to substitute our value of y and our value of x in order to find c. Once we find c, we can substitute c back into this original function, and that would be our axis of symmetry. So there's basically 3 steps involved. Step number 1, substitute x and y. Step number 2, find the value of c. And step number 3, substitute c into the original axis of symmetry equation. So let's do a quick explanation. So our y represents our q value, and our p represents, or rather our x represents our p value. So in this case, we are dealing with the asymptotes. Asymptotes are very important when we're dealing with hyperbolic functions. They are used quite frequently. So the first step is to always identify your asymptotes whenever you're dealing with a hyperbolic function question, because you're going to use them quite often. So step 1, substitute y as q and x as p. So once we've substituted them, we'd end up with q equals p plus c. Step number 2 is to solve for c. So if we were to solve for c, we'd end up with c equals q minus p. And our last step is to substitute c back into the original. So therefore, we'd have y equals x plus q minus p. whatever that value is. So that's how we can find our axis of symmetry for a hyperbolic function. Now let's do the same thing but for our negative axis of symmetry equation. So we know that step number 1 is to substitute Q as Y and P as X. So this is going to be Q equals negative P plus C. Our step number 2 is to solve for C. So C would end up being Q plus P. From here we can substitute C into the original and we would end up with Y equals negative X plus Q plus P, whatever that value is. Now, this value of C represents where the axis of symmetry line cuts the y-axis. So it's essentially the same thing as a linear function, except we don't find our gradient. The gradient is always given to us as either 1 or negative 1. Another important thing to take note of is that the axis of symmetry lines intersect at the point PQ. So if we have our positive axis of symmetry and our negative axis of symmetry, these two lines would intersect at this point P and Q. Those would be the coordinates of their intersection. Something else that's important to take note of is that our asymptotes also intersect at this point. For example, let's use orange to denote our asymptotes. So our vertical asymptote and our horizontal asymptote. So we'd have x equals p and y equals our q value. So as you can see, our asymptotes are quite important. Now let's move on. Point number 7 deals with reflections. So 7.1 is to reflect the graph about the x-axis. Now we know that whenever we're reflecting the graph about the x-axis, the value of x remains the same, but our value of y will change. So what we'll do is, in order for us to change the value of y, because keep in mind this entire function represents y, all we do is we multiply that entire function by a negative. So we'd have negative f of x, which will then give us negative 1 over x minus 2 plus 3. So we're basically substituting the entire function by a negative because that entire function represents our y value. So you therefore have y equals negative 1 over x minus 2 minus 3. So we've multiplied the entire function by a negative, and this shows that the value of y has changed. Now, if we want to reflect in the y-axis, our value of y will remain the same, but our value of x is going to change. Now, we know that in order to change our x value, this is the only value that represents x, not the entire function. All we need to do is substitute a negative x. So, if we want to change x, we just substitute negative x. So, let's do that. So, we have f of negative x equals 1 over, now wherever we have x, we substitute in brackets negative x, and we write everything else as is. Therefore, our reflected function is going to be, let's just use y equals 1 over negative x minus 2 plus 3. Now, let's not leave the bottom as a negative x. So instead of leaving it as negative x, we are going to change it to positive x. Now, how we can do that is by by factorizing or taking out a common factor. So as you can see, the common factor is negative. So let's extract a common factor. That's negative x plus 2. So once we take out our common factor of negative from negative x minus 2, we end up with x plus 2 in brackets. And then we know that 1 over negative gives us negative 1 on top. So we can conclude that y equals negative 1 over x plus 2 plus 3. So a quick recap is when we are dealing with reflecting about the x-axis, we change y by multiplying the entire function by a negative. That will change y. If we want to change x, we substitute in brackets negative x in place of our x. Nothing else changes. Now, once we've put negative x into the position of x, we then need to factor out that negative and divide it with our value of a, which is our numerator, so that we don't have a negative denominator or that we don't have negative x. Now, let's move on. So, in the space over here, before we start with our question, let's try and sketch a function, more specifically a hyperbolic function that has our x, our y intercepts shown clearly, our vertical, our horizontal asymptotes shown clearly, our positive, our negative axis of symmetry shown clearly. So basically we're sketching a function, or rather a hyperbolic function, whereby everything that we've previously discussed is clearly visible. So let's start with our x and y axis. Now this represents our x-axis and this represents our y-axis. Now let's sketch the function. Let's see, what function can we create? Let's make it y equals 1 over x minus 3 plus 1. Instead of minus 3, let's just make it minus 2. So that's our function. Now, before we start sketching our function, we need to determine in which quadrants it's going to be. So because a is greater than 0, we know that it's going to be in quadrant 1 and quadrant 3. Now we need to determine our intercepts. Actually, before we do our intercepts, something important that we need to get is our asymptotes, not our intercepts. So let's get our asymptotes. So we need the value of P and our value of Q. So let's start with Q because it's the easiest. So our value of Q is positive 1. Now our value of P, because we see x minus 2, we're going to take out the opposite sign. So instead of taking out negative 2, we're going to take out positive 2. An alternative approach would be to equate that to 0, solve for x, and you see P is positive 2. Another approach that could be used is x minus 2. Now to write it in the form or the position of our formula, so x minus, now we know this is going to be positive 2, because negative times positive will result in x minus 2. So that then shows us that this is going to be positive 2. So now that we have our value of P and our value of Q, let us draw our asymptotes. So I'm going to start with my vertical asymptote, which is P, and that is by 2. That is at the position 2. Now, I'm going to draw my vertical asymptote, and that is at the position y equals 1. So let's label our asymptotes. So that's going to be y equals 1 or q equals 1. Let's just make it y instead of q. And that is going to be x equals 2. Okay, now we have our asymptotes. We can put in our point of intersection of our asymptotes. And that point of intersection, or that coordinate point, is 2 and 1. Now that we have our asymptotes drawn, let us sketch our function. So because our function within quadrant 1, which is this area over here, does not intersect the x or y axis, we can just draw a random curve within this quadrant, making sure that our curve does not pass or intersect our asymptotes. That is our curve in quadrant 1. Now, if you notice, our curve in quadrant 3 is going to intersect the x-axis and the y-axis. So before we sketch it, we need to first find our x-intercept and our y-intercept. So let's start. So our x-intercept is when y is 0. So let's substitute y as 0, solve for x. That's going to be negative 1 equals 1 over x minus 2. From here, I'm going to swap. I'm not going to use the previous method that I used because I feel like swapping is easier. So I'm going to swap the denominator on the right with the numerator on the left. So that's going to be x minus 2 equals 1 over negative 1. If you don't want to swap, all you can do is use the method I previously used, whereby I cross-multiplied, expanded, and then divided. So this is going to give me x minus 2 equals negative 1. From here, I can take negative 2 to the other side, becoming positive 2. So I have x equals negative 1 plus 2, which is 1. Now my x value is 1. So let's put that in. Now we need to find our y-intercept. So our y-intercept is when x is 0. So all we do is we substitute x as 0 and solve for y. So that's going to be 1 over 0 minus 2 plus 1, and that gives us 1 over negative 2 plus 1, and negative a half plus 1 gives us positive 1 over 2, or you can write it as 0.5. So positive 1 over 2 is going to be around here. That's going to be our positive 1 over 2 or 0.5 value. So we know that our graph needs to intersect our y-axis at this point and our x-axis at this point. And our graph can never pass or intersect or cut our asymptotes. The graph can go extremely close to the asymptotes, but it will never intersect or cut it. So, a quick recap. We started sketching our function by first drawing our x and our y asymptotes, or you can call it your vertical and your horizontal asymptotes. After we did that, we determined the shape of our function, so we know which quadrants they're going to be in. Once we did that, we found our x and y intercepts, and then we plotted both our curves. Now let's put in our positive and negative axis of symmetry lines. So let's use the space on the left to find our axis of symmetry lines. So we know that the first one is our positive axis of symmetry line, which is y equals x plus c. We know that our y value is our q value, which is equal to 1. And our x value is our p value, which is equal to 2. So let's substitute y as 1. We can substitute x as 2 and plus c. From here, we know that c equals 1 minus 2, which is negative 1. So we therefore have our positive y-axis, or rather our positive axis of symmetry as x minus 1. Now let's do our negative one. So we have y equals negative x plus c. We know that our x and y values are still the same. So this is going to be y equals 1. Bring down our negative sign, and p equals, or x equals 2 plus c. From here, we know that c equals 1 plus 2. So c is going to be equal to 3. We can then substitute that into our original and have y equals negative x plus 3. So these are our axis of symmetry lines or equations, whichever you want to call them. So let us plot them. Let's see, what colors have we not used? Let's use green for our positive axis of symmetry. So our positive axis of symmetry cuts the y-axis at negative 1. So negative 1, let's make it somewhere around here. So this is going to be negative 1. And we know that from our example, from our theory rather, we know that our axis of symmetry lines intersect where our asymptotes intersect, which is this black point over here. So we've got 2 points. All we need to do is connect both the points. So that is our positive axis of symmetry. That has an equation, y equals x minus 1. Let us now draw our negative axis of symmetry line. So let's erase this a bit and clean this up. Now our negative axis of symmetry line is going to be similar to our m less than 0 or negative gradient linear function. Now from the information we are given, or from the information we calculated rather, we know that c is positive 3. So let's make positive 3 over here. We have our point of intersection of our asymptotes. So we have our 2 points needed to draw our straight line. So let's take our ruler, connect the 2 points, and sketch our line. Now that is our negative axis of symmetry line that has an equation y equals negative x plus 3. Let us now clear up all of our excess information and then discuss what we have drawn. Okay. So we have a greater than 0 hyperbolic function. We know that whenever a is greater than 0, our function is always going to be in quadrant 1 and quadrant 3. So because a is greater than 0, we have quadrant 1 and quadrant 3. We also have our asymptotes, which are p equals 2 and q equals 1. We have our x and y intercepts. So x-intercept has an x value of 1. Our y-intercept has a y value of 0,5. And we've got two axes of symmetry equations, which are represented by y equals x minus 1 and y equals negative x plus 3. So that is all the information that we have now drawn. We also have a point of intersection of P and Q, or of our asymptotes, which has a coordinate 2 and 1, which is this point over here. Now that is everything that we have drawn. This is our hyperbolic function. If we were drawing a hyperbolic function whereby a was less than 0, our curves would have been drawn in quadrant 2 and 4.